All right, today we're going to talk about lexical love, rediscovering the power of lexical search in RAG. Maybe a quick intro. Hi, I'm John Berryman. Um, I I got started in aerospace engineering like 2 decades ago, and it was fun and all, but the things that I loved were software and math. So I got into a different field. I decided to get into technology. I worked for a large portion of my career in search technologies. I got the opportunity to write a book on the matter with colleague Doug Turnbull. And that was a blast, but I decided writing a book is a horrible thing to do to yourself and decided never to do that again. But fortunately, because I'd written a book, I got a chance to work at GitHub and I worked on code search there. We built the next generation of code search 2 generations ago, so it's kind of done its thing. And I was very fortunate while at GitHub to be in the right place at the right time to work on Copilot when it was just kind of coming out of the research lab at the time. And that was a great experience. I learned tons and tons about large language models and how to build stuff using them. And so I wrote another book. And then as of almost, but not quite a year ago, I left GitHub and I've created my own search consultancy named Arcturus Labs. It's a large language model consultancy, Arcturus Labs, and there's the website. So if you guys are interested, then look me up. Now, of course, all these lightning talks are kind of for an ulterior purpose. I do have a training class coming on Maven in the middle of June. If you guys are interested, I would love you guys to attend. It is building LLM applications from principles to practice. That, of course, is the URL and QR form if you are looking at a recording of this later. But the principle is this. There's so much stuff coming out with large language models every day. New models, new frameworks, new ways of doing everything, so it seems. But the course, I'm really trying to dig into the fact that at its core, there are basic principles, there are underlying core principles that kind of make all this stuff a lot easier. You don't have to worry about every single little thing that's coming across in the news every day. A lot of it's hype. And if you're grounded in the basic principles, it becomes a lot better to build things out of large language models, a lot easier, and a lot easier to generally know like what kind of things you can build out of large language models. All right, so let's dig into this talk. Semantic search in RAG. Well, there is a presumption, it seems today, that semantic search is the way that you do RAG. And it's easy, right? You chunk up all the documents. You can use some sort of embedding model, sentence transformer, some BERT-like model to get all of your documents, all the chunks into the same vector space, stick it to a vector store, and at query time, you just take your query, whatever it is, and embed it into the same space and pull out the documents. Seems like a really good way of building RAG. If you look at any tutorial online, it's basically this. And it's cool, right? Because the old-fashioned lexical search, which is what we're going to be talking about, is doing like old, exact token matching, whereas semantic search is based on meaning. And it's true. It really is true. You can do some really cool stuff with semantic search, but there are challenges. For one thing, the very cool thing that you can do with semantic search, sometimes you don't want to look up things by just meaning. You want to find the exact terms, such as like product IDs or people's names, or phrase matches. Like I want to find a movie title with this phrase match, or jargon that's been introduced into the lexicon since whatever model you're using has been trained. All these things are really challenging to do within embeddings and with vector search. And if you do run into some sort of issue with semantic search, uh, not being able to find the documents that you want, how are you going to fix it? It's hard, right? Probably your embedding model is not quite right. So you got to retrain it. When you retrain it, you got to dig up a lot of good examples of what good matches look like. And then you kind of got to pray and cross your fingers that it's actually going to work, because you're not going to know until you actually wake up, reindex all the documents again and try again. Also, filtering with semantic search is kind of clunky. It's hard to like slice and dice stuff from the data set. So let's actually look at that in detail. How do you filter things with semantic search? Well, option one, okay, you take your query, you give it a search, you get back results. But option one inside search, what you could do is, well, you do a semantic search first, and then whatever results come back, this is the nearest neighbors, and whatever results come back, you just filter them down. Well, the problem with this, you could have a strange search that whenever you apply your filter, narrows it down to like being no results at all. I'm looking for cheap diamonds. So diamonds with a price lower than, some pretty low price. Maybe they're actually in the index, but the nearest documents to diamonds, you automatically, the semantic of diamonds is rich stuff, very expensive. And so when you do a semantic search for diamonds and then filter, you might just filter out all your results. You have to, play games to get all the results you need. You could do the opposite. You could actually filter first and then semantic rate. But then think about what happens if we filter first to all the cheap things in our entire index of whatever it is, and then sort all those documents. This is brute force search, brute force re-ranking. You sort all the documents after you filter it. If it's a large data set, then this is going to be way, 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 way slower than the semantic search that we're talking about right here. So filtering stuff just kind of implies problems. The index that we use for semantic search is just not really cut out for filtering things. So in this talk, we're going to do these things right here. First off, I'm going to give you like a body slam introduction to lexical search. And we'll teach you kind of everything you know, as much as I can compress into the next 30 minutes or so, about how lexical search works and how to stand up a search engine using Elasticsearch. Then we'll give you an example about how you can use this to actually create a different type of RAG with lexical search instead of semantic search. We'll discuss some of the problems, because even though I like lexical search, it's got its problems too. And then we'll point to marrying the two, the happiest of all worlds, trying to do something better than either of the individual things with hybrid search. All right, let's learn lexical search really freaking fast. 3 subchapters to this: indexing, search results, searching, and formatting results. Now, lexical indexing, you can think of it as a data store, just like vector indexing, just like a database for that matter. It has all the typical things that you would expect a data store like a database to have. So booleans, integers, floats, dates and times, and it's even got some more exotic things. You can do searches based on geo shapes and points and intervals of times, and you can have even have compound types, or arrays, and objects that you can store and search on. So it's a really flexible. Lexical indexing provides a really flexible form of search. But the star of the show, though, is the text itself. You have 2 forms of text. One is keywords, which is just exact match on this string must be exactly this. But the really cool one is text, which you process into an array of tokens, and that allows you to find all the documents that have a certain type of words in it, what types of words that you're looking for. All right, so let's get into the index in itself. The first thing you do is you bring your documents to the index, and they go through a stage called analysis, which converts a string, and this would be like, in reality, this would be, thousands of words. This would be your entire document. Could, in principle, be a book. But it converts your string into an array of normalized tokens. First, it goes through character filtering, which you do simple things with just the letters. uppercase to lowercase. If you got like a diacritic above a word, cafe just turns into CAFE without the hyphen over the word. Tokenization after that. You split, and you can split on, you can assign it to split on whatever you want to. So you can do some really intricate things here, but by default, it'll split on things like white space and punctuation. Notice that our punctuation is gone. That's not a token. Stop wording. We take all the words that are super common and we just cut them out. They're not useful for the meaning that people are going to be looking for. So we let go of them. And then finally, stemming, which you take every adjective, every adverb, every verb, and there's common endings: jumped, jumping, jumps, jumper, and you normalize it by basically chopping off the ending. And occasionally you do some monkey business like this to replace the ending with something that's common. But it's just an algorithm so that all these different words are mapped down to one word. This helps you match on meaning. Even though you're matching on tokens, you're still going to be able to match on meaning, just not quite in the same way that we're doing a semantic search. And now that we have everything turned into tokens, lexical indexing stores documents inside an inverted index. What does that mean? Well, let's say you have 3 different documents and we've pulled out, all their tokens. We invert the document. So like, let's look at this right here. It's got these tokens in it. We invert the tokens, and every token becomes a lookup key for an ordered list of all the documents that contains this. Notice that this is document 43, and you can see all, this would be a list of every word we've ever run across in our indexing, and you can see that 43 is in these particular words. The reason we do this is for really quick speed of search, and we'll see that in just a moment. But first, we are done with indexing. Let's take a comparison. With indexing, with semantic search, you have to actually do a little bit more work. Documents are pre-chunked. Finding the right chunks is actually kind of a finicky thing. If you like chop important information in half, then that's going to be bad for your RAG application. With lexical indexing, there's no chunking, so that's quite a bit easier. With semantic, the indexes are often a lot larger because every document has several chunks, probably, if it's a large document, and these chunks are not tiny. It's vectors that are like 2,000, potentially 2,000 some odd floating point numbers, sometimes even longer than that, and that's a lot of information. Lexical search is very, 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 very compact. So you might find a lexical index that ostensibly has kind of the same type features, but is like half the size. With semantic search, the data is very opaque. You have vectors that have meaning, but not meaning to humans. Whereas with lexical search, the data that you're indexing, it's kind of munged words, but it still looks like words. So if you really want to get into it and understand how things work, you can actually understand how the matches are being made. All right, subchapter 2, search. So lexical search is really fast, and it's easy to see why. Let's find all documents that contain the word fox. All right, well, that's easy. This is just a lookup. Remember, we inverted the index. So it's as if I've done all single word searches a priori when I created the index. But you can do more creative stuff. I can search for brown and fox. Well, that's just pulling out these 2 vectors and merge sorting them together. Merge sorting them so that you don't, you got to make sure that it's indexes that appear in both vectors. Or you can do like an OR search, fox or dog. So that's unioning these 2 vectors together. Super fast operations. So you can see how search is really fast. Effectively, we've done all the searches that you could possibly do a priori. But it's not just that you can find documents that match Boolean searches quickly. You can also sort them according to relevance. Basically, semantic search, you're looking up documents based on meaning. But lexical search, you're also looking documents based upon meaning. It's just a different way of doing it. So consider this. If we look up brown and fox, we would like the documents that have more brown and more fox in them to rise to the top. And we want documents like if we have the brown fox or something like that, we want to make sure that words that are super common don't influence the score. And the way that we do this is with a scoring method called TF-IDF, which basically means term frequency divided by document frequency and inverse document frequency, which really just means, count the number of times that the word appeared in the doc. How many times did brown occur in any particular doc? How many times did fox occur in any particular doc? And you also divide that by how many times the document, that word occurs across all your documents. So if for some reason brown is just super common, then we're going to pay more attention to fox in scoring the documents. And this is a really good way of bringing the best results to the top. The extra cool thing that we won't really get into too much, besides just alluding to it, is that with multi-field search, with semantic search, you're just matching on meaning. It's just, you've got words, and that's it. With lexical search, you've got multiple fields. You get title, description, all this stuff. And you can boost and say, well, the title is more important than the description. Or you can have like a numerical popularity score, and you can say popularity influences the match of a document. So you can do all sorts of neat little things with lexical search that you really can't do with semantic search out of the box. Now, as we're at the end of the searching subchapter, let's compare the differences here. With semantic search, you're looking at things based on the approximate nearest neighbor. It is in meaning space, and that's really cool. But it's also opaque, and you have like effectively kind of one field that you're dealing with. You can filter stuff later, but whenever you filter it, it is in different steps, and that can sometimes run into trouble, like we talked about earlier on. Now, with searches with lexical search, you search on matching tokens. It is a form of matching by meaning, and it's not quite as good, but it is still, it's what's powered the internet for most of the internet's history. So it's also not that bad. Cool thing when you start dealing with lexical search is you get multiple fields. You can deal with them simultaneously, and you can do filtering on multiple fields in the same data structure without having to do this post-filtering thing that gets you into so much trouble with semantic search. Finally, with semantic search, relevancy is distance. That's it. If you don't like it, you better reindex with a different embedding. Lexical search, you can play all the games you want with relevance. And while the search is live, while the same documents are indexed, you can change, debug, move things around without all the effort of retraining anything or applying different types of boosts, or without doing the same types of stuff that you do with semantic search, having to retrain, reindex. And finally, the results subchapter here is the last cool trick that lexical search has up its sleeve is how it formats the information coming back to our RAG applications. With lexical search, you get at first what looks basically just like what you get with semantic search. You get your results set. You can pull back the top in documents. Maybe a little extra bump that you get here is you also get not just the top in documents, but you also know how many documents actually match the search, period. So that might be useful information for RAG to know about. More interestingly is that you have aggregate information. So with lexical search, it can actually look through all of the result sets, all of the potentially matching results, not just the 100 nearest ones, and it can start doing aggregate analysis of all the other information in all the other fields. So for example, if we're doing some sort of document search and the documents are categorized like you see here, then we can count how many documents are inside each of these categories. If we have another field, maybe we're doing like Airbnb and we have like prices, then one thing that we can do is have a distribution plot of all the prices that are inside this result set. With lexical search, you also get snippets. This is kind of like search time chunking. When we indexed the lexical search, we didn't have to chop anything up. We just sent the whole document in. But at search time, there are several different approaches to pulling out the portion of the document which is most useful. So think of it as kind of like search time chunking. You also get highlighting, which is basically a way of saying, this is the chunk that mattered, but also these are the word matches that we thought were important. It is direct word matching, so maybe a little bit clumsier, but no, might still be useful. All right, so with lexical results, we have differences with semantic and lexical as well. This top bit is kind of similar for both sides. We have semantic search, chunking, and with semantic search, you have to chunk the documents first, and you have to make sure that each chunk has the appropriate metadata. With lexical search, sorry, I got my wires crossed. With semantic search, the results have the chunks and have their metadata. With lexical search, the results, you have the full document that can come back, but you also have all the snippets. Effectively, this ends up being the same information that comes back on both sides. With semantic search, there are no facets because all you can do is select the top 100 or whatever documents. You can't actually do any analysis on all the documents that might have matched the search. With lexical search, you can do a lot of really cool statistics and you can incorporate that into your RAG application. It's kind of a neat effect. All right, so that's how lexical search works. How would we stick it into RAG and end up with something that's kind of neat and different from what we can get with semantic search? All right, so let's consider a scenario. We have a home items shopping assistant, and we're going to allow our users to interact with the assistant, chat with it, and find items that they might want to purchase. Now, all of these items, I wanted to add some extra filtering capability here. So all these items have limited availability. They're only available in certain states. So if our user is from Tennessee, where I'm from, then we want to make sure that we actually have a filter. We don't just match all the documents. We've got to also use a filter for only the documents, only the items that are available in Tennessee. For this example set, we are using WANs, which is a really fantastic data set. If you guys want to play with any type of search, I would highly recommend this for indexing into, semantic search or vectors or lexical search. It is an e-commerce product data set. It is home items, furniture, appliances, and it's also got some really neat benchmarking labels if you wanted to do some other work in there. It's a really large, it's a very realistically large data set. I think, as a matter of fact, it is realistic. It is their inventory, and it has several important fields for us. It has the product name, which this is how you add a mapping, add a schema into Elasticsearch. You say the product name is going to be a text field, and by the way, it's English, which means that Elasticsearch knows how to chop it up and do the analysis we showed earlier. There's also a product class, which is keyword. We're not going to chop it up at all. And within these two things, the product name and the product class, we can chop up. We can have a subfield so that we have the product name is English, but the subfield, we're not going to use the same analyzer. We can chop it up a different way so that we don't, for example, chop the ends of the words off and do any of the normalization like that. Product description is another English field, and rating count is an integer field. I've also added this availability field. It's just a list of whatever states are available. All right. So now that we're getting ready to build this RAG application, we have a Python bit here. We have a Python function called high-level search, and it's got 4 arguments, whatever the user or whatever the RAG application wants to search on. the availability, which is going to be the user's state, product class, min rating, and the number of results. We implement this by basically building Elasticsearch search. So you can let your eyes blur just a bit, but if you're actually interested in getting into Elasticsearch, then this is how you put together a query that searches over these fields. You say this is kind of how you do your Boolean search. You don't use ands or ors. You use must or should. And so with Elasticsearch, you can say, well, whatever query string we're searching, the bare minimum, it must match in one of these two fields. However, it should also match these fields. If it happens to match, have a phrase match, you can do different types of searches. If it happens to have, a substring that you're searching for present in product name or description field, then we're going to boost it up. So it'll still be within this set, but it's going to be boosted higher. But also we can, remember we had this exact field that didn't have the same analysis, didn't chop off the ends of the words. If it matches with the exact words, that's also a good indication that it's better. So we're going to just add more points into that. These all add up. Inside the Python function, we're going to check and see if availability is being supplied. If so, then we'll add this to the search query. It's just a filter. The product class is being applied, we'll add that to the filter. If the min average rating is applied, we'll add that to the filter as well. And finally, whenever the search executes, we have to make the text presentable to the model. So we're going to have a tool for the RAG application. Whenever this tool is called, it's going to present something that looks roughly like this. It's going to say, here's the product, here's its name. Importantly, here's a list of classes that are associated with it. The model is going to be able to use these. And here's the description. So the model has an idea of what's going on. We're going to give 10 results back by default. And that's that. The next bit is formatting the results so that we include some of the statistics here. Remember, we can provide aggregate statistics for everything that matched. And with Elasticsearch, here's how you do it. You say, here's our product class. One of our fields is product class. I want you to find all those fields and all the results. And this basically says, keep track of the top 10 such product classes and look at the counts of how many documents match in each of those fields. And so that information gets formatted in the response as something that looks like this. Facet counts, and we just list out, how many products occurred in desks or TVs or kitchen mats or whatever. And this is really valuable information for the RAG application. It can look at this information and understand, okay, well, maybe I can clarify my search and go back. All right, so now we have, for our large language model application that we're building, we have the application side. It's time to make the large language model side, which is tools. Our agent itself is going to be the definition of the tool, the system message, and basically the runtime to keep asking the user questions and keep track of the messages. The tools is just something that looks exactly what we saw earlier, but this is me explaining it to the large language model rather than implementing it in Python. I tell a large language model that it has access to a search catalog function. Tell it what it's all about. I tell it the different fields that it can use, and I say very explicitly when it should use these fields. And if that wasn't enough, I'm also giving it a system message, which is more high level. I'm saying, hey, you got to say that at the beginning of all your agents, you're a helpful assistant. But how are you a helpful assistant? Well, you do a lot of different stuff on behalf of your user. Your users are going to ask about things like this. And here is a typical method for navigating the catalog, providing useful information back to the user. And something that you guys are probably familiar with from being in the field, but if you're not, you should take my class. This is how you build the large language application itself, the RAG application. Effectively, it's a loop. In this loop, the user is going to give a message to the application, and we're going to assemble it into something that is useful for the large language model to review. We're going to pull the system message, the tools, and the user's history together, send it to the LLM, and the LLM can either choose to take the tool execution path or the completion path. If it chooses to use our search tool, then we'll actually call out to the Python method, get the information back in the form that I just showed you, stick that back into the prompt, and now the large language model, I guess it could keep searching again, and we'll see cases where it might, or it can convert this information to something that's useful to the user. It could be a simple text response, or if we have a more involved application, it could be a pretty UI that demonstrates some of the products that they could buy. All right, well, our application is going to be really simple. We have our helpful assistant right here, who I hope you guys are familiar with, and you have the user. Hello, how can I help you? So the user says, my back hurts all day from sitting here. So what's going to happen here? Well, hopefully the RAG application is going to say, okay, this is a good opportunity to start using search. And indeed it does. We'll go through several examples, but I built this application, and these are these are examples that are going to be pretty common in the use of the application. But I've instructed the model that it can use search multiple times, either in parallel or in series. So in this case, it ran 2 searches in parallel just to get an idea of all the things that might exist in this index. A cool thing that is already happening here is because of the way I defined the function, I'm already filtering all the results that come back from lexical search according to the user's state. I want to make sure that these items are available in the user state. So I'm already, what we said you might trip over with semantic search, we're already getting past that with lexical search. Now there's a lot of things that the agent can do here. In this case, it's did a parallel search to kind of, branch out and do multiple things at once. It can also do series search. You can say, I want to find standing desks. And as it looks at the results, it can say, oh, okay, there's different types of things here. So I'm going to change my query to make it more specific and get something that might be more useful for the user in the context. But a really cool thing that we have here is that in the response from this search tool, we have provided extra useful information. This aggregate statistical information that you can't really do with semantic search. We can say that for whatever search you did here, standing desk, we have 553 desk items, but we've also got all this other stuff, and a lot of it's kind of cruft. Plant and telephone and office chairs. This is not quite. These are documents that mention standing desk but aren't standing desk. So the agent can use that to clarify the search by applying its own filters on top of this. So you can have the query and the filter and the agent in charge of filling those out. And so the agent might follow up. Can I recommend this standing desk? The user can keep engaging, like I only want the best rated desk. So the agent has access to all sorts of filters. Just another cool thing that you could do, and you're not going to run into the same trouble like the cheap diamond issue, because all of these fields are effectively simultaneously searched. And I didn't actually build this into my little application that I built when I was testing this out, but you can do all sorts of other cool stuff here in principle. Right now, the query field that I'm providing to the model is just plain text. But Lucene is the library upon which Elasticsearch and everything else in lexical search these days is built, and it's got its own syntax. And the model has been trained on all sorts of documents that talk about Lucene syntax. So it's possible that you could say, "Dear model, you have access to Lucene syntax. Go to town." And it could potentially rewire the whole notion of relevance as it used the app. It could boost, rather than like filtering by lower priced desks, it could just like boost lower priced desks. It can do all sorts of stuff in principle. All right, so that was how you build all this stuff. But there are limitations of lexical search. And so let's dig into those a little bit. I know that this is a dress. You know that this is a shoe. And we all know that this is a dress shoe. Now, the unfortunate thing is that lexical search thinks that this is a dress shoe. Not ideal. And the reason it's doing this is because lexical search operates on bag of words. It's effectively, when you do that document inversion step that we showed you earlier, it's got basically a bunch of random tokens. Every document is a random set of tokens, and it does have extra capabilities where it can like still wire together phrase matching, stuff like that. But it's not quite the same as semantic search, which has a notion of, meaning. So lexical search doesn't get synonyms. It doesn't know that a riverbank is a different thing from a bank where you have money. It doesn't understand, oh, that was homonyms. It doesn't understand synonyms, which, like, a gorilla suit is the same thing as a monkey costume. You have to search for, the exact matches. And it's kind of clueless about negation. So if you say this is not a gorilla suit or something like that, then it just sees gorilla suit still. And these are the very same things that semantic search excels at. So womp womp, it appears that we are stuck. I want filters and facets and boosting from lexical search. It's really powerful. But the meaning, and you can still search by meaning in lexical search, but the ability to search by meaning with semantic search is, when it's working right, it's a lot more accurate. It's a lot more intuitive. If you've got the right embeddings, then it's going to be, that part of it is going to be a lot more satisfying. I want both though. So are we really stuck in this, one of these two options? Well, maybe, but we're at least working on it. And there's we know that there's a problem, and so there's a lot of effort to try to move things towards a truly hybrid solution. One thing that's being explored, which is, it gets towards the solution but it's not there, is Splayed, which basically you take a lexical search engine and make it pretend to be semantic search. The way you do this is by looking at the words and using an embedding model to take the words that are actually in each document and guess at which words should have been in this document. If you have a document about the gorilla suit, then it should have had tokens like monkey costume, stuff like that. So it makes it better to have, higher recall for your search. Something that's happening on the other side, inside the HNSW data structures that power semantic search, Acorn is a way of basically carrying around that filter, attaching the filter to the vector search itself, so that you don't have to do a post filter. You can do the filter as you're navigating this tree of results. But it's got its own problems. It kind of it's liable to miss documents. It's and to get kind of in corner cases that are not great. I've gotten the feeling that it's just not quite there yet. And the last thing on my short list here is Superlinked. Now, whereas the previous two are actual, things that are ongoing in research, Superlinked is a startup, and I'll at least put them here because I think they're creative. I can't attest to them. I haven't actually used them myself, but the idea is really neat. Basically, they're able to, instead of having one document field and embed everything into that, all the text into, that effectively one field, you have your semantic field. Superlink says, all right, well, you've got some description field, we'll embed that with, this part of the vector. You've got a location field, we'll embed that in part of the vector. You've got a price field, and it's going to be a smaller embedding, and we can kind of pack all these things together. And when they do that, they can piggyback on any vector, in principle, any vector database that already exists, do the same nearest neighbor that would normally happen, because their embedding vectors are designed so that it, that works correctly. And then they post filter, and you could potentially run into some of the same post filtering problems. But since they have all these semantic subfields, it's much more likely that you've already narrowed down the semantic space to like the cheap diamonds that I was talking about earlier. So it's, all these things are kind of helpful. But in the meantime, we still do have hybrid search, classical hybrid search, and maybe it's not so bad. For example, there's just a couple of options, and there's nuance to all this. But one thing that you can do is whenever the query comes into your search engine, so the first thing that you do is query expansion. If it's you're about to send it to the lexical search, but the user searched for gorilla costume, you can ask a large language model, what other queries should we ask of the search engine, and then it'll put in monkey suit, whatever the opposite one I said. It'll put in several different queries. We can get all those search results back from lexical search, have pretty darn good recall, and then after that's done, we can apply semantic re-rank. So we've still got, very much recall based on traditional lexical search, and then precision is basically the job of semantic search to take the top 100 results and get it back into a really much better order. Another thing that you can do to get the best of both worlds in principle is whenever our query comes in, you can send it 2 directions, or you can send it even more directions than this. You can, use query expansion and do all sorts of stuff. But the 2 main directions are lexical search, hit up Elasticsearch, and then semantic search, hit up Weaviate, something like that. And then when this returns results and that returns results, you can use something like reciprocal rank fusion to take all these results and combine them back together into the best order based on whatever occurred here in the ranking that they occurred in these result sets. And I guess it's probably obvious at this point, I'm a pretty big fan of Elasticsearch itself. It's got all the pieces that you need to build a lot of these things. So obviously, it's got this box right here. Everything I've showed you is lexical search and Elasticsearch. It's how it started. But it's also got query expansion. It's in the paid tier. You can also use a large language model, like I said, to do query expansion, and it would be just as good, maybe better. Vector indexing is an add-on with Elasticsearch, but a lot of data storage systems have added vector indexing. Approximate nearest neighbors. So that's it's got the ability to do hierarchical navigable small world data structures with semantic search, and it's also got the ability to do like brute force resorting like you would want here. And then if you wanted to combine the results together, it has this as well in the paid tier. And make sure, you've got all these cool things that you can do. Make sure that you update RAG so it can be hybrid as well. Out of the box, when most people put RAG together, they say, all right, here's your search tool, and it's got 1 argument, query. But there's no reason that you can't take your search tool and say, here's the exact match argument, and then here is like the semantic match argument. And I built this too. The large language models do a really good job about understanding, the user is looking for a movie with this title or this, this phrase in the title, and it'll use the correct field in the tool for that. And if you say use, I want to find movies about something else, it'll use the correct field for that, as long as your tool description is really well set up. All right. Well, 2 minutes past our official time, but I'll stick around if you guys have any questions. And actually, I can't see if anyone still exists on the other side. So hopefully you're still there watching too. But thank you very much. Do take a look at this, see what you think about it. If it's right for you, then I hope to see you at the course. And yeah, unmute and feel free to hit me up with any questions you have for the next few minutes. Satoshi said it's 5:30 a.m. in Japan. Wow. What is semantic re-rank? So in my talk, there is kind of like the dichotomy with semantic search and semantic re-rank. I guess that's the bigger dichotomy of semantic versus lexical. But within semantic, semantic search is actually using a data structure that's meant to do vector search, and it's super duper fast. It's really a cool data structure. Look up hierarchical navigable small world. But if you're in a situation where you're like doing a filter first, basically you're already throwing away your ability to use that cool HNSW data structure. So the only option that you have after you filter down documents is to do a brute force search after that. This is actually not so bad if your filter is something smarter than like this. Let's look at all the cheap documents, the cheap products. Because that's going to be a huge set, and you can't actually one at a time compare all the query vector with the document vector for each one of the results. But if you're using lexical search for your filter, as we showed in the last slide, then semantic re-ranking, where you take the embedding of the query and you've already saved the embeddings of all the documents, it's only going to be like 100 comparisons or maybe 1,000 comparisons, something like that. So that's what semantic re-ranking is. Does anyone else have any questions? Juan says, what do you think about replacing BM25 with sparse embeddings such as Splayed or Minicoil? I would not recommend a replacement. But I think they are a really good augmentation. In my mind, so I've played around a little bit with Splayed. I've got a blog post about Splayed where I make kind of a hackneyed version, a broken down version of Splayed for Elasticsearch. And the words that come out of Splayed are not like synonyms. So I said it's like monkey suit for the original document and gorilla costume for the Splayed words, the synonyms that come out of it, but it's not quite. It might be like monkey suit, and it might be like party comes out over here, or something that's even a little bit further away. Occasionally, not so rarely, you get surprises. But they're associated with a score as well. So I mean, like if you have a really unusual word, the score at least does kind of push it farther away. I would use Splayed for casting a wider net and getting more results back. I would, with lexical search, I would boost higher if the phrase or the user's exact words did occur in the document, the original document, rather than Splayed. And then I would, like in the Cadillac version, I would do semantic re-ranking on the results that come back from that. So wouldn't get rid of BM25, but I would combine them. Rajendra asked, injecting synonyms during query expansion, do you think word to vector would be a good option? Well, so you might have to unmute and make sure I'm getting the word to vector right, but word to vector returns vectors, and it's not going to be those of the sparse variety. It's going to be dense vectors, like you might index into Elastic, into a vector index or something like that. So how would you get the synonyms from the vectors that come out of? Oh, okay. Parsing word to vec. So basically, you use word to vec to turn every one of the words into vectors, and then you can look up based on similarity other words that are similar to that. Yes, you could do that. I would still probably go the route of Splayed, which is doing something kind of like that, but with a bit more recent technologies. Like the word, I guess depending on how you wanted to do it, the word to vector is going to not have the knowledge of the full context of the document. Whereas if you have an embedding vector for the full document, it's going to have like the context that bank means the place where I put money, as opposed to bank meaning the edge of a river. So I'd still go with Splayed instead of injecting synonyms from word to vec. Anyone want to unmute? Any other questions? Going once. Going twice. All right. Well, thanks so much.
Yeah, yeah.
Go.
Thanks for the answer on the Splayed, but have you heard about the mini coil, the one that Woodrun released recently? It apparently uses BM25 and it adds like some sort of semantic understanding on top of BM25.
So have you? Yep. I haven't heard of it. So if you have anything, what's the highlights that we should know?
I don't know if we could use it as a replacement of BM25 for this sort of lexical search. Or
Does
we
it
can
convert
use it as
everything
an
into?
improvement.
Does it convert everything like into sparse vectors, kind of like Splayed effectively does?
It's similar, yeah. I get it similar. It's like a mixture of both worlds. Like it's played with BM25. I haven't really had the time to dig more on it, but it looks promising. Here's
Okay.
I'll share the article here on the chat.
Yeah, please do. Thanks for the new information. Qdron quadrant. All right. Well, going once, going twice. Thank you guys so much for showing up to the talk. I hope you enjoyed it. I enjoyed delivering it. And yeah, hope to see you guys in the class. See ya.
Thanks, John.